Hey there, Braves. So this week we're going over how to balance chemical equations, and we're talking about chemical reactions in general. Um, I've been kind of promising you that we would get into some basic chemistry stuff beyond just like atoms and the periodic table, and this is really what we're going to get to. It was a short quarter. We did kind of have 2 weeks in the middle there that were really, really short. They were 2 days long, so we lost a lot of learning time, and we're obviously not going at the same speed we normally would in a given year. So basically, this is about as deep as we are going to get when it comes to balancing chemical equations for this school year. And this happens to be one of the more difficult things for students because they let themselves get scared, nervous, and then their brain shuts down and they don't process what's actually happening. Balancing equations is actually really easy to do. All you're using is multiplication. So if you can do multiplication and you can count, this should be a fairly simple process. It's not simple in that you're not going to immediately know the answer right away, but you should be able to figure it out after kind of squirreling around a little bit back and forth on either side of the equation. So if you are afraid of math, don't worry. This is actually fairly easy math to do. And if you love math, well, this is going to be fairly simple, and this might not be as fun. I don't know. I'm just spitballing here, talking to my computer screen. Okay, so let's go ahead and talk about this stuff. So chemical equations. A chemical equation is just I'm going to charge my pencil while we're doing this. A chemical equation is just a representation of a chemical reaction on paper, and it puts a numerical value to your reactants and your products. Your reactants are the things that you're mixing together to get the chemical reaction to happen. And your products are the things that you get after those two things react. It's fairly simple. The coefficients, which are the numbers that come before a molecule, tell you how many of those molecules you have or need. And the subscripts, the little tiny numbers that are at the bottom, tell you how many of each atom are in that molecule. So when we go to balance these equations to make sure we conserve mass, because that's what we do here. It's all about the conservation of mass. What we're going to do is count up the coefficients and the subscripts to figure out how many of each atom's on each side, and then we adjust the coefficients as we need to. If that was a lot of gobbledygook for you and that was all over your head, don't worry, I'm about to explain and go through all of that. So the coefficients and the subscripts just tell us how many atoms we have. And when we balance an equation, the coefficients are telling us in what measure of each molecule we need to get a complete reaction, so we don't have any leftover reactants. So if I take baking soda and vinegar, there's a certain amount of vinegar I can use with a certain amount of baking soda so that when I mix them together, they get completely used up and turned into the things that we're trying to create. So there won't be any leftover baking soda and there won't be any leftover vinegar. If you put too much vinegar in and not enough baking soda, well, you will have some vinegar left over. You won't have completely reacted away all of your reactants. So what we're actually doing here when balancing equations is we're actually figuring out how much of each chemical we need to get a complete reaction at the end. So let me kind of give you an example here and I'll talk through it. I'm going to take everyone's favorite chemical reaction. At least it's what I would assume everyone's favorite chemical reaction is, and that would be combustion, because that means we're burning stuff and blowing it up. So, right? You all like burning stuff and blowing things up. I think you do. At least you like watching it. Okay, so I'll go on ahead and let's write this out. So I'm on the eraser. We'll use a very common fuel, which would be glucose, C6H12O6. And we add that to oxygen, O2, and that goes to CO2 plus H2O. Okay, well, let's talk about a few things first. Here are the subscripts. I'll circle those in red. Boom, 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 and boom. Those are all subscripts. This is telling me that in glucose, this molecule right here, I have 6 carbons, 12 hydrogens, and 6 oxygens. It's telling me I have 2 oxygen atoms stuck together here. It's telling me I have in CO2, I have 2 oxygens. It's telling me in water, I have 2 hydrogens, okay? The subscript always goes after the atom that it's related to. Okay, now, because of this knowledge right here, I can easily count up how many atoms I have on each side, because it's telling me right here on, the equation. So what I like to do when I'm trying to balance equations is I like to make a dividing line to start off with. I'll make a dividing line, and I'm going to run this over here. All right, so I've got a little table underneath my equation. I probably should have moved this up a little higher so I had more space to write. I apologize. Okay, now I'm going to write down, I got my carbons, I got my hydrogens, I got my oxygens on this side. Carbon, hydrogen, oxygen. And I'm going to keep a tally of how many of each atom I have on either side. This is going to help me balance my equation. Okay? All right. So on the left-hand side, the reactant side, by the way, these are the reactants, and these are the products. And this thing right here indicates that it's a one-way reaction. We can't go the other way. Now, if you saw an arrow that looked like this, then that would mean that you have a reaction that can go back and forth, like the reaction that happens inside of a rechargeable battery. Cool? Okay, that's not what we have here, though. So this is a one-way reaction. Once we react this stuff, it's not going back to sugar and oxygen again. You have to do special stuff to it to make that happen. Okay, so let's count up some of our atoms on either side of the equation. Okay, so carbons on the left-hand side, we have 6 of them. How many hydrogens do we have? We have 12. And the number of oxygens we have is 8. We have 6 from the glucose molecule, and we have 2 right here from the free-floating oxygen. All right, okay. Now, on the right-hand side, the product side, what we get at the end, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. All right. So you can see that this is not balanced. There's a problem here. We have 6 times more carbon on one side than on the other. We have 6 times more hydrogen on one side than the other. And we have 60%, almost double, not 60%, almost double the number of, actually it is double. We have more than double of the oxygens on the left hand than the right side. Good job with the mental math there, Mr. Clemens. Okay, so what do we do? How do we fix this? Well, this is where the coefficients come into play, the numbers that go before the molecules. So what we want to look over on the right-hand side, we need basically 6 carbons on the right-hand side. We only have 1. Well, what molecule can I add extra of so that we have that? Well, that would be the CO2. It's the only molecule on the right-hand side that has carbon. So that's the one that I'm going to multiply. So I'm going to go over here. How many carbons do I need? I need 6 total. I have 1 now, so that means I need 6 CO2 molecules. Just like that. So what I'm doing is I'm multiplying CO2 by 6. So what that does is it changes my total tally. So now I have 6 carbons on this side. And if I count up my oxygens, 6 times 2, see there's that 2 there? 6 times 2 is 12, plus 1 over here from this single oxygen on the water, that makes 13. So now I have 13, oops, that was wrong, that was hydrogen. Now I have 13 oxygens, okay, which is more than I have on the left-hand side, but we'll worry about that in just a minute. Okay, now what do we still have that's out of balance? Our oxygens aren't balanced and our hydrogens aren't balanced. So what can I do on the right-hand side to adjust the hydrogens? Well, very simply, I can add more water molecules, the H2O. Okay, so I have 2 now and I need 12. Well, 6 times 2 is 12, right? So that means I need 6 6 water molecules to get my 12. So there you go, 6 right here times the 2 underneath the hydrogen. That gives me a total of 12. And this bumps up the number of oxygens that I now have, because you notice that oxygen is both in the water and in the CO2. So I have to adjust my tally for oxygen as well. So I have 12 oxygens coming from the CO2, and now I have 6 oxygens coming from the H2O. 12 plus 6 would be 18, I believe. So 18 oxygens is what I have. All right. So now comes the easy part. The balancing of the oxygens on the reactant side, this side of the equation. This is really easy because oxygen's over here all by itself, which is why we balance this one last. Just makes it simpler for all of us. So we have 2 oxygens here. We have 6 oxygens here to make our 8. So the one that we want to mess with without throwing everything else in balance is the O2. We need 10 more than what we have. So if I were to multiply the oxygen by 5, would that be enough? No, that would be 10 plus 6 would be 16. So I need to multiply it by 6. 6 oxygens, O2s, 6 times 2 gives me 12, plus the 6 right there from the glucose molecule. That gives me the 18. So I cross this out, 1, 8. Now if I look at my equation, I have 6 carbons on the left-hand side, 6 carbons on the right-hand side. I have 12 hydrogens on the left-hand side, 12 hydrogens on the right-hand side, and then 18 oxygens on the left and 18 oxygens on the right. So you can see that I didn't do any crazy math here. All I did was use multiplication and addition, plussing and multiplying. That's it. It was straightforward. So this is what we're practicing this week. And I am going to give you a couple of, well, practice problems I'm going to work through here in front of you until we kind of get the gist of how to do this. So I'm going to give you a couple more. All right? Okay. So let's do that. Scoot down here to the next slide. Pop up my pencil stuff. All right. So we'll do the first one, which you can't necessarily see because my big head is there. So let me move that over to the side. Boink. And let me go on ahead and move my pencil stuff up to the top so it's out of the way. All right. We'll start off with number 1. So number 1 would be H3PO4 plus KOH, potassium hydroxide, and the hydrophosphate there comes out. Okay, and that gives us K3PO4 plus water, H2O. Okay, so how do we balance this? Same thing we did last time. So I'm going to go on ahead and draw my table here. And I'm going to go on ahead and write down an entry for each of the atoms that's on either side of the equation. So my hydrogens, which I'm going to potassium, phosphorus, my oxygen, and my potassium. All right, H, P, O, and K. All right. So let's go ahead and count them up. On the left-hand side, I've got 3 hydrogens and 1 hydrogen, right? Because that's a 1 over there on the KOH. So there's 4 hydrogens here. There's 1 phosphorus. There are 5 oxygens because I've got 4 coming from the H3PO4, and I've got 1 from the KOH. So that'd be 5. And I have 1 potassium. All right, do it on the other side. Got 3 of these. 1 of those. 5 oxygens and 2 hydrogens. Okay, so generally what I like to do is go for the things like potassium and phosphorus first, especially when I've got something like your water molecules and whatnot that make it easy to adjust some of the other things later on. So let's go ahead and knock out our potassiums. That one seems pretty straightforward. So what we're going to do in my blue, you notice there's 3 over here, but there's only 1 over here. So we simply just need to multiply the 1 by 3, and adjust our totals. So potassium now jumps up to 3 on this side because it's 3 times 1. But now we have to adjust our oxygen and our hydrogen. So we have 4 oxygens here. We have now 3 oxygens here because there's only 1 there, and now there's 3. So 3 times 1. Okay. So 3 plus 4 is 7. Is that correct? I think so. And hydrogens just jumped up. So we have 3 here and 3 here now. So that becomes 6. All right. Next thing to balance. Let's see. It looks like got 1 and 1. Hydrogen and oxygen are the only things that are out of balance. And can we do that with just the water? Let's find out. So we need 6 total hydrogens. So if I multiply this by 3, the water by 3 over here, 3 times 2 is 6. So that balances me out there. And then 3 times 1 for the oxygen would be 3 plus the 4 there. That gives me 7. So now when I look at this equation, I have 6 hydrogens on each side, 1 phosphorus on each side, 7 oxygens on each side, and 3 potassiums on each side. So voila, there you go. That is a balanced equation. We only needed 3 of these, and we needed 3 water molecules, and that's all we had to do to adjust this equation and make it balance. Pretty easy, right? All right, let's go ahead and go over another example. I need a bigger eraser. This might take a minute. Potassium. We have potassium plus 2, 3 plus B. Okay, this one's going to be really simple because you have 2 elements that are just standing over there by themselves, and that makes balancing really easy. So let's go on ahead and make our table. Boing, boing. And let's go on ahead and count up what we have on each side. So there's our potassium, boron, oxygen, potassium, boron, and oxygen. Okay, and how many do we have on each side? We have 1 potassium on this side. We have 2 potassiums on that side. We have 2 borons on this side. We have 1 on this side. We have 3 oxygens on this side and only 1 on that side. So it looks like oxygen might make this one a little bit tricky, just knowing what I know. So how about we balance the oxygen first this time? Because oxygen's not over here on an easy molecule for us to balance. Okay, so looking at this, what do we need? We need 3 more, so let's multiply this by 3, okay, because it's, single right there. So 3 times 1, that gives me 3. 3 times 2 gives me 6 potassiums. So I got 6 potassiums. All right. Looking at my equation now, what is out of balance? Well, my potassiums are definitely out of balance, and luckily on the left-hand side, it's just sitting there by itself. So if I go over there and I multiply that one by 6, well, now that balances and I don't have to do anything else. Pretty awesome, right? That's what makes it so beautiful when they're sitting there by themselves. All right, and then I look over here on the right-hand side, what is still unbalanced? Well, it'd be my borons. I need 1 more. So if I multiply that by 2, this moves up to 2. And voila, I am balanced. Must be all that meditation I do. All right, so there's another example for you. I actually think I'm just going to go over 2 more examples because I think 4 examples total are probably enough. So let me erase this really quick. Okay, so the next equation we have is hydrochloric acid plus sodium hydroxide. And that goes to sodium chloride and water. So this is, well, we won't get into what type of reaction this is. I don't need to throw too much at you at once. So let's go ahead and do it. HCl plus NaOH goes to sodium chloride plus H2O. Make my table. And let's count up what we have on the side. Hydrogens, chlorines, sodiums, and oxygens. Oops, H. All right, HCl, Na, and O. Okay, so what now? Let's count them up. On the left-hand side, my reactant side, I have 2 hydrogens. I have 1 chlorine. I have 1 sodium, and I have 1 oxygen. So not a lot. On the right-hand side, I have 2 hydrogens. I have 1 chlorine. I have 1 sodium, and I have 1 oxygen. Well, by golly gee, guys, that looks like it's already a balanced equation. What do you know? That works out well. Hooray us. All right, so last example. We'll go on ahead and get her started. Sodium plus sodium, nitrogen, and oxygen. So nitrate probably what that's called, and then got this plus N2, and nitrogen, N2 for nature. So yeah, there you go. So nitrate, yeah, that's right. So let's Na, nitrogen, oxygen, Na, oxygen, nitrogen. On the left-hand side of the equation, I have 2 of these. I have 1 of these, and I have 3 of these. On the right-hand side of the equation, the reactants, sorry, the products. I have 2 of these. I have 1 of these. And I have 2 of my nitrogens. Okay, so this one might be a little bit more complex. So let's see what we might want to change first. How about the number of nitrogens we have on the left-hand side? Let's see what that does to the overall equation. Seems like the thing to do first. So if I go on ahead and multiply this by 2, this will bump my nitrogen count on this side because it's 2 times 1 up to 2. And now that balances, but it adjusts my sodiums. So now I have 2 sodiums plus the 1 over here. So that would be 3. And then my oxygens jump up to 6. Okay, so now let's see if we can balance this other side since we got our nitrogens balanced out. So looking at how many oxygens we now need, we need 6 total. And since it's NaO1 here, we'll go on ahead and multiply that by 6. So 6. It's not going to let me work. Doing that, my oxygens on this side bump up to 6, but now my sodiums become 12. 1, 2. All right. So everything is now balanced except for the sodiums. I have way too many on this side. Okay, well, I've got 2 sodiums here, so I need a total of 10 more. So the great thing is I just put a 10 in front of the sodium here, and then that's 10 plus the 2 here, and now I have a balanced equation. So you can see, even myself, sometimes I have to pause and think about how I do this. If you feel like you're getting stuck in a loop and you're just multiplying on either side a bunch of times, you can't balance it, try starting back over and starting with a different component. Sometimes that helps. So there you go, guys. That is basically balancing equations in a nutshell. It's fairly, like I said, it's fairly straightforward. You just want to make sure you have that tally table at the bottom, work through the multiplication and addition as you need to, and you should figure it out. Now, the last thing I'll tell you before I let you go and get started on your practice this week is that when we get to the end of this, what this is saying is that we need 10 parts of sodium right here and 2 parts of this sodium nitrate in order to get 6 parts of this and 1 part of regular just atmospheric nitrogen. So if I were to be making a solution, or I were to be weighing out these atoms or weighing out these molecules to mix them, I would want, an equal part. I would want 10 parts sodium, 2 parts sodium nitrate. So it lets us know kind of the ratio of chemicals we need to yield our products at the end and not have any leftovers. So that's what you guys basically just figured out here, just doing some basic math. Coolio. All right. Well, with that, good luck on your assignments this week. If we get a chance to go outside and enjoy ourselves in the sun, I recommend that you do it. Vitamin D is one of the most important vitamins you can get for your immune system. And as I've said multiple times before, especially if you're one of those people who's worried about COVID and how you will react to it, well, the more vitamin D you get, the better you'll react to COVID, the more protected you'll be. And that's been pretty well established in medical science since this pandemic started. So go out and get sunlight. You need it. And you can't really catch the virus when you're out in sunlight because it dies pretty much immediately. So go outside. All right? All right. Later, Braves.